Continuing on, we want to talk about polyprotic acids. So poly means many, protic means protons. So polyprotic acids are molecules that can donate more than one H+. So these are molecules that contain more than one hydrogen, and they can basically lose those hydrogens. The thing is, each hydrogen is still lost via one donation. So for example, H2CO3 is carbonic acid. So there are two hydrogens in one molecule of carbonic acid. Both of those can be donated to, say, a water molecule. And they are going to happen one at a time. This basically comes from the fact, you think about back to like kinetics, the idea of elementary steps. Each time a hydrogen is moved, basically from the acid to the base, that is a collision. That is one elementary step. These hydrogens are not going to be lost in like the same single collision or something where, say, you both are transferred. The other thing to consider is that base molecules only generally can accept one hydrogen at a time, and in general, water can only accept one hydrogen, one H+, period, right? There's no H4O2+, you just make hydronium. So what has to happen is basically the first hydrogen has to be donated to one water molecule, and the second hydrogen has to be donated to a different water molecule. So you make two unique hydronium atoms in the process, or hydronium molecules, sorry, in the process of donating those. But they each happen sequentially, and both of those processes are equilibrium processes. So when we're looking at formulas for acids, we kind of want to get kind of some practice and some kind of familiarity with identifying when an acid is polyprotic. And not only that, but how many hydrogens could potentially come off of that. So nitric acid, HNO3, if we want to try to be parsing out polyprotics, we can look at the Lewis structure. HNO3, we could also just look at the formula because there's only a single H in the formula, so that is going to be just one. We call that a monoprotic acid. That's, everything we've been dealing with so far for the most part has been monoprotic or been talking about those ideas. So that there's a single H on an HNO3 molecule, and that can come off in that way. Phosphoric acid, H3PO4. When we look at that, we would think, hey, we can probably lose 3 hydrogens, and that is consistent with looking at the Lewis structure. There are 3 hydrogens that are attached to oxygens in this molecule, and basically each of them can be lost sequentially. Again, they're all going to be lost one at a time, making each time a new conjugate, that can then also continue to lose those hydrogens. CH3COOH, we can see we do have more than one hydrogen in this formula, but only one of these is an acidic hydrogen. And if you remember, when we're dealing with organic acids, this COOH is indicative of that molecule being an acid, and the hydrogen in the COOH is the acidic hydrogen. That is the hydrogen that can be donated as an H+. The hydrogens that are attached to carbon are not going to be donated as H+. And in fact, hydrogens bonded directly to carbon are never acidic. That's just that bond is not going to break in that way. You'd be left with a C-, which is not very stable. And so that bond's pretty strong. It's just not going to break. The barrier is really high. One of the things, if you remember, acid-base chemistry is really fast. That barrier is really high to break a CH bond. So that's very slow chemistry. But the OH over here that we're dealing with here, that can break and donate as an H+. So we can always, the chemical formula can be a little misleading sometimes, but that's also one of the reasons why we write organic acids with this COH part to highlight that's the acidic hydrogen. For water with H2O, when we look at the molecular formula, we may think, hey, there's 2 hydrogens here. Those could definitely go. At this point in time, that's just something you need to know, that even though there are 2 hydrogens in water, you're only going to ever lose one as an H+, right, and turn it into hydroxide. If you remember, we said hydroxide was never an acid. That was one of the first things in chapter 14. Still the case. The first hydrogen can go, and the second hydrogen is not leaving hydroxide. You're not gonna, that is not acidic, just like we had with the carbons. That's just the barrier to break that bond is very, very high. It's just not gonna happen. Because the deprotonation of polyprotic acids happens in sequence, you really can kind of think about it as functionally different acids each time. So phosphoric acid is H3PO4. So we have H3PO4, that's our starting acid. Overall, there are 3 hydrogens that can come off of that, and they come off one at a time. So the phosphoric acid donates to a water molecule, making a hydronium, and you produce dihydrogen phosphate. H2PO4 is the conjugate. That H2PO4 can then come in, and now that is the acid. Okay, so that is the acid. It can donate to a separate water molecule, make another hydronium, and then you would produce hydrogen phosphate, which can be, again, another acid, donate to another water molecule, make another hydronium, and you get phosphate in the end. So these are 3 distinct processes, and we can think of these as there being 3 unique acids that we're starting with. And so those acids are going to each be characterized by their own Ka, right? The Ka being the equilibrium constant of when they react with water. And as you take more and more hydrogens off, we can see that this Ka value is decreasing, right? We start with 10 to the negative 3. Phosphoric acid, H3PO4, is a decently strong as far as weak acids go, right? 10 to the negative 3rd, that's not bad. That second one is 10 to the negative 8th, and the third one is 10 to the negative 13th. That is about as weak as a weak acid can get. You can't get much worse. 10 to the negative 14th is the limit of how low you can go because that's water. And so that's really what we're kind of looking at here, that this is much weaker. And so the way we can understand this is you're trying to take an H plus away from an anion, right? You'll note that these things are conjugates, so they are negatively charged. And they become more and more negatively charged. So they are worse at donating an H plus, right? You're having to remove positive charge away from an anion. You also lead to the creation of these really highly charged anions as a result. Phosphate at 3-, that's really negative. That's going to be relatively unstable. Generally, things don't want to have that much negative charge on them as a molecule. So it's always true that as you donate hydrogens, it gets weaker and weaker and weaker as far as the acid goes. So another correlation, sulfuric acid is a strong acid. Only the first donation is strong. After that, the second one is weak. So let's look at an example of what is the pH of a 0.25 molar solution of phosphoric acid, H3PO4. So we just saw the Kas. This is a case where I want to get the pH of a solution of acid. So, you know, it's a polyprotic acid, but I'm only going to be dealing with them one at a time, right? I have one donation at a time. I'm going to be creating some hydroniums, and the Ka, I can look it up for phosphoric acid for just the first deprotonation. You'll note there's the 1 there to denote it's the first one, 7.52, 10 to the negative 3rd. Okay, so this is going to be a weak acid. So the process of determining the pH is going to be, I'm going to need to use an ice table. It's going to be set up like my general ice tables for these solutions, for weak acid solutions. The shift is going to be to products. I'm going to make my H's. My Ka is going to have the same general form that we've seen for all acids. We can plug our values in. We can solve for X. You actually cannot use an approximation, so you got to use a quadratic formula. I'm not going to make us do that, but you do have to do that. But you can figure out what the equilibrium concentrations are. You can figure out that, you know, it's 0.04 molar for hydroniums and for the H2PO4-, and 0.21 is left for the H3PO4. Okay, so if you are given this, you can figure out just using what we've learned previously about weak acid pH. So nothing too crazy on this one. And yeah, you can figure out the pH would be 1.4 from that hydronium. So if we think about what's going on in the actual solution, so I have phosphates, so each one of these molecules is a phosphate molecule, and then I have some waters. And so when the H3PO4 goes into solution, some of them react with the water, and they donate that proton to water. And the ratio is for every 20, so the ratio that is shown here is accurate. For every 25 of the original molecule, so here's the original molecule, for every 25, 4 of them donate an H plus to water, becoming the conjugate, right? Becoming the H2PO4-. So that's how much of that is created. So now I have this new acid, this H2PO4-, that can lose a second hydrogen. So this is where polyprotic acids are different and unique from what we've seen previously with monoprotic acids. H2PO4- was created in the first reaction, and this can now react with water to make more hydroniums. I have an equilibrium constant here, it's 10 to the negative 8th, so it's a weak acid process, and I can work through this process. You'll see one of the things though, this is a much lower Ka than the initial K1 that we saw for phosphoric acid just a little bit ago. So we would expect that this acid is weaker. It will have less of an effect on changing the pH. When we go to set up the ice table, one of the other things we can note is that the initial concentration of hydroniums is not 0. It is 0.04. Right? There is already some hydroniums that have been created due to the initial deprotonation of my H3PO4 molecules. You'll also note I have a lower starting amount of my acid here. So that means if I have it's a lower concentration, there's fewer possible H3O+ to make. There's already some product, so the shift to reach equilibrium will not be as strong. It won't be as big of a shift. We can go through and solve all of this. The Ka looks different, but we can solve it, and we end up getting that X is equal to 6.23 times 10 to the negative 8th. So if we think about what we really care about for pH is how is the hydronium concentration changed? So we had an initial hydronium concentration, right? It was 0.04, and we are adding 6.23 times 10 to the negative 8th. Functionally, we don't change it, right? It is still just 0.040 molar for the hydronium concentration, meaning the pH is still the same. So the purpose of this is to show that because subsequent, right, it's a sequence of deprotonations, because the second or third deprotonation is so minimal, right? It's a weaker acid. There is less of it. There is already some hydronium, so the shift to reach equilibrium is smaller. All of those things work against it such that anything after the first deprotonation doesn't matter, right? The pH was 1.4 after the first step. If you just had ignored this second step, solving this requires more work, and our answer hasn't changed. What is the pH of the solution is still just 1.4. So yes, there is really some tiny concentration of this, 10 to the negative 8th molar, but it just doesn't matter at this point in time because it doesn't affect the properties of the solution. The first deprotonation has really affected it, and the second and the third, that does really happen in solution, just isn't going to be noticeable as far as the pH goes. So we had this kind of depiction we showed that I started with 25 molecules. For every 25 H3PO4s, I made 4 H2PO4-. If I wanted to maintain kind of the appropriate ratio, I would make, for every 4 million H3PO4s, I would get 1 additional hydronium ion. And so that's where you can see that that secondary deprotonation just really doesn't matter when you're dealing with this. So whenever you are trying to figure out the pH of a polyprotic solution, you only need to deal with the first deprotonation. Yeah, so you can almost always ignore it. Anything beyond that first deprotonation, because that second deprotonation is going to be weaker. You have a lower starting concentration. There's already some hydronium. Also, one of the things about log is because you've already moved the pH to something like 1 point something or 2 point something, you have to remember log is a times 10 scale. In order to go from, say, pH 2 to pH 1, it has to get 10 times more acidic. And that's just going to be hard to do when the solution is already kind of acidic. It's really easy to get 10 times more acidic than pH 7 because it's not very acidic at all, right? So you can get those kind of moves. So you don't need to worry about that when you're dealing with something. Now, if you started only with H2PO4, then that's the only acid in solution, and then you would have to deal with that. You would have to deal with that deprotonation. What I'm saying is when you put a polyprotic acid into solution, you only need to be concerned about the first deprotonation. So if this is the molecule you put into water, you do need to be worried about its deprotonation. It's going to be enough to affect water because all of these things won't be true, right? Because there's nothing else in the water at that point in time. You're going to make some hydroniums and affect the pH. All right, one more video down. We are now halfway through the set of videos. Looking for any more questions on participation 1014. Got a couple more videos. See you there.